Okay, my name is Paul, thank you for coming, and I'm going to talk about my research and such. So, before I get started, I'm going to tell a quick story about an anecdote that was going around the web last year about what it's like giving a presentation to Jeff Bezos, who's the CEO of Amazon.com. So if you guys haven't heard of him, Jeff is sort of a Steve Jobs, Bill Gates quality mind, really, really brilliant guy. And he sort of spends all day thinking strategically about the tech sector, and he gets bored really easily. So something he's done is he has banned PowerPoint on the Amazon campus. You are not allowed to show him slides. He'll kick you out of the office if you do, which is like, wow, what a concept, right? So this person on the web was asked to give a presentation to him, and he figured out, like, he'd seen a lot of presentations where Jeff gets bored and says, come on, get to the point, and it's like terribly embarrassing for your career if that happens to you, right? So he found, he came up with the secret. After seeing a few bad presentations, the secret is to give Jeff's brain something to do while he's sitting there, like listening to you talk. So he makes up his outline for his presentation, and then he just deletes every fourth bullet, and like leaves that for Jeff to figure out. So while he's talking, there's all this information missing, and Jeff's brain is like, oh, and making the connections, and he's like, great presentation. So, and it works apparently. That like he was really, anyways. So this was in my mind when I was sitting down to do this talk, because we've all sat through enough PowerPoints to last a lifetime, especially whenever I go to a conference and there's 15 talks in a row of slides. I start daydreaming about being at Amazon where there's no PowerPoint. When I was thinking about what I was going to say, I immediately started to be tempted to think about dense technical information and tables and graphs, and like maybe I'll need the whiteboard to try and write stuff, even if I just no. Go away, and then once you let go of that, it becomes like free. There's this whole blank slate, so it's kind of cool. So I hope this works. I'm going to just talk for 30 or 40 minutes about my field and my research, and try and paint a picture of it, and hopefully it'll be interesting. So my name is Paul. You guys all know me, I think. I'm in the 5th year of my PhD at this point. My research is on ICT and environment. ICT is Information, Communications, and Technology. It means Information and Communications Technology, rather. It means the high-tech sector, electronics, cell phones, cell phone networks, communications, televisions, home entertainment, gadgets, basically all of the high-tech stuff. I'll define that as ICT, and I might use technology as a shorthand for that. The study of the environmental impacts of ICT is a new, small, fairly fragmented field. This is the field that I find myself in. There's people working on it from various different angles, but not a whole lot of people, and it's sort of still figuring out what it is, I suppose. And mainly what I'm going to talk about is what this field is, and what are the problems and how you can attack them. My personal background, I have a computer engineering background, so I come from the land of numbers and code, and that's sort of still how I approach problems. So that colors my perspective, obviously. The tech sector is where I sort of used to study and work, and I got kind of bored of it, and so I'm here now to engage in bigger questions, and I'm sort of studying my own previous home from the side, which allows me, it's nice because it lets me bring a fresh perspective, and that's something a lot of us in this department have, I think, as we approach our problems, not from within a disciplinary context, but from a problem we want to solve, and then we sort of look and grab tools from various disciplines and throw them all at the problem. So that's what I'm doing here. You guys are all doing that probably in your own research to some extent. So what I'm going to talk about in this talk is first outline the origins of the field. How do people start asking these questions about ICT and environment? And then the meat of it is what's the current state of knowledge? What kind of questions are being asked? How do you answer these questions? What kind of research is being done? How does my own research fit into it? That's just a small part of this talk. And then finally, where's it going in the future from my perspective? So I hope this works, and I hope you guys enjoy it. So the origins of the study of the environmental impacts of ICT. To understand this, you have to understand the tech sector. And you guys are all familiar with, you can see with your own eyes, the rapid development that we have in the tech sector, the sort of emergence of new products, things getting faster and smarter, smartphones, tablets, laptops, all more powerful than they were. These are continuations of trends that have been running since the 1970s. We used to have gigantic room-sized computers that could do very, very basic arithmetic, and now we have incredibly sophisticated cell phones that can do incredibly powerful computation. There's exponential growth going on, and it's been going on for 30 or 40 years, and it's going to continue for at least another 10. This has enabled rapid disruptive change, which you guys have all seen in our lifetimes. It's affected the economic structures in many societies. It's been an instrumental part in the transition away from heavy industries towards service economies. It's enabled new behaviors, new products. It's caused a splash, you might say. So this has been a major feature of the modern era, I would say. And what a lot of research has been doing is trying to make sense of it. It's been a bit of a struggle for meaning, to understand what's been happening to our society because of all this, and then what does it mean, what are the consequences of this, and is there something we should do about it, or not? Is it good? Is it a good thing? Is it a bad thing? This is the kind of the common questions that come up in the research. And I found two common perspectives in especially some of the older work in this field, which you could call pessimistic and optimistic. Pessimistic, the sky is falling, technology is destroying the planet, it's ruining our societies, it has very, very bad environmental impacts, there's toxic chemicals inside, we're using way too much energy, it's going to dominate our energy consumption, and it's destroying traditional sort of things that we need in our societies, like connections between people, and so on and so on. And there's also the optimist. We're living in a brave new world. Technology is going to solve our problems. It's going to make us grow our economies, which will help us solve our problems. It's going to lead to sustainable development. It leads to dematerialization. We can do things digitally instead of using physical products. It lets us do things more efficiently. We don't waste energy now. And we should just keep going full steam ahead. So I guess in the late 1990s, these two schools of thought were kind of fighting with each other. It's people saying, hold on, hit the brakes, and other people saying, brave new world, goes full steam ahead. Both of these perspectives are kind of out of date at this point. Neither of those visions has come true in the 10 years or so since this discussion was happening. Instead, technology has just become part of our lives, and it's an industry like others. It's a special one because of its disruptive effects, but it's not so special that it can't be dealt with in the same way that we deal with other problems, I suppose. So a lot of the interesting work has dropped the questions of good versus bad, and is actually focusing on applying more traditional research methodologies to this industry. But I'll point out that it's worth keeping an eye out for pessimism and optimism when you think about ICT and environment. If you read our news articles, for example, the New York Times just had a recent series about data centers, talking about how much energy they use, and it was total sky is falling pessimism and completely off the wall in terms of its characterization of what's actually going on. It was really bad, but it got a lot of buzz, because this sort of thing is common. It's just data is taken out of context to paint a really negative picture, and the things that they say are not necessarily untrue, right? There is a lot of energy being used, but there's a lot of energy being used in other industries as well. So you sort of have to watch out for people who have some sort of desire to say that the world is going to end because of this. But also at the same time, watch out for people who are just taking an uncritically rosy view of the future, and saying technology is going to solve our problems, because neither of those things really are very useful. So that's kind of where the field has started. And the current state of knowledge, I'm going to break it down into 4 different research areas, which I've been forced to grapple with as part of my PhD. They come from different disciplinary traditions. They're all asking different questions. They're all trying to do different things. They're using different methods, but they're working on the same kind of area. So sometimes they'll use each other's results. Sometimes they'll interact, sometimes they won't. But all of them, I'd say, have some relevance to this overarching question of how do ICT and the environment interact? How do those things fit together? So there's four areas. The first is engineering lifecycle assessment. The second is energy services and energy planning. The third is public health and environmental science. And the fourth is social science. So those are the 4. And all 4 of these have active research going on attacking this problem, but from very different angles. The first is engineering lifecycle assessment. Being that I come from an engineering background, this is what I gravitated towards first. When I started researching it, I found this stuff first. And so the goal of this kind of research is to quantify impacts. It's to tell you how green something is in terms of various dimensions, such as kilograms of CO2, greenhouse gases. So carbon footprinting is an offshoot from life cycle assessment. It's an accounting method. You have to add up all the contributors to an impact, all the materials and chemicals, figure out their damage to the environment in all kinds of different dimensions, and then do a big sum. One of the main purposes is to help you target your efforts. If you're working on a big system and you want to reduce the environmental impacts of it, you have to know which pieces of it are the big pieces first before you start attacking them. Otherwise, you have no idea if you're going to make any impact at all. So the end goal is to influence consumption, decision making, and to make systems more efficient. Life cycle assessment emerged around the 1970s, 80s. The first uses were beverage packaging by Coca-Cola. They were looking at plastic versus glass versus metal, I suppose. And energy systems were in early use as well. And the methodology has been developing more and more, and now it's used on all kinds of products and systems. And carbon footprinting has been a way of sort of streamlining it to look at a very specific subset of impacts. And you can actually calculate the carbon footprint of just about anything. So what do we know from this perspective? There's been lots of work done on electronics products using life cycle assessment. Some of my PhD research has taken this approach. So we know that the carbon footprint of the global ICT sector is about 2 to 3% of the global total of anthropocentric GHG emissions, which is not a huge amount, but not small either. It's nothing like transportation or agriculture, but it's not negligible. A common comparison is made is the aviation sector is also 2 to 3%. So if you care about aviation emissions, you should care about tech emissions as well. We know that a desktop PC has a life cycle carbon footprint of maybe 200 kilograms of CO2 over the course of its 4-year lifespan. So there's the number, right? And the problem with LCA is like, what does that mean? What do you do with that number? So the answer is 200, 100, 200, 500, therefore whatever. It's not a very large number. It's, again, not negligible. I think about 600 vehicle kilometers driving is the equivalent to one desktop PC. So that's, most people who have a car would get that in a few weeks or months. And this is over a span of 4 years. So your electronics, if you have a lot of them, it may add up, but it's again, same sort of idea. Small, not gigantic, not negligible kind of in there. We know that for a lot of major large products, like desktops and televisions and servers, the electricity from using the devices is the dominant thing to worry about. So you should think about things like the materials that go into it, the manufacturing processes, transportation, end of life. We know that transportation is a very tiny slice. So the fact that these things are shipped from overseas doesn't matter. We know that the manufacturing impacts, especially raw materials, especially semiconductors, which is the very highly energy intensive brains of the computer, those things count for quite a bit. But overall, I'd say the majority of the impacts come from electricity to run the big energy hog devices. And that depends on the context, which kind of grid you're in. Here in BC, we have fairly green electricity, so the manufacturing impacts of our electronics will be higher than the use phase. But overall, the use phase tends to be the largest. So my own contribution to this research was to try and improve our knowledge of the manufacturing impacts of a lot of new products. There's been not a whole lot of coverage because these studies are really complicated to conduct. So there's been studies of desktops and laptops and servers and monitors, but there wasn't anything of an iPad or an ebook reader or a smartphone. And it's really hard to compare across studies. So it's hard to know what's greener than what. So this is a piece of work that I did where I took about 10 different products and I analyzed them all. I took them all apart and I weighed all the pieces and I mapped them into this industrial emissions database of parts and did a comparison. And I was able to show that a fairly obvious result in retrospect, that big things have bigger impacts and small things have smaller impacts. Which, okay, duh, but until you actually run the numbers, you can't say that for sure. It turns out there's a pretty reliable linear relationship between mass and embodied emissions, greenhouse gas emissions. So the lighter your thing is, the less emissions were made in the production of it. The heavier it is, the more emissions, linear. So it means you don't really have to worry about your cell phones or your iPads or even your laptops. Their impacts are there, but you should worry about your televisions and your servers and your desktops. That's where the bigger impacts are going to be. Unless you have a whole lot of these things and their mass starts to add up. But that's one thing that I was able to show. What we don't know, how's my time? Okay. What we don't know in this field is there's a lot of issues around data quality, data uncertainty. We're working with very old data, and the methodology is really rough, I would say. It's way rougher than most people would realize. So I would argue it's questionable whether these numbers really mean anything at all. I think there's a lot of work to be done shoring up the methodology. I think there's an issue here in terms of how you define impacts, what questions you're asking. Because even life cycle assessment, the method, it can tell you carbon footprint, but it can also tell you acidification potential or eutrophication potential or ecosystem damage and all these different indicators. And you have to figure out what you're measuring and what you're reporting and how are you defining impact. And what most people do is they're given, so you have product A and product B, and you run an LCA on them and you get 20 different answers. The impact is this if you're asking for carbon footprint, it's that if you're asking for ozone depletion. How do you make sense of that? And what if they don't? What if one of them is better in some and worse in the others? So what tends to happen is everyone just throws out everything but carbon footprint, which is that a valid thing to do? I don't know. That's an open question. There's not much coverage for new products. The data's old. It's problematic. LCA is very focused as well. It doesn't have a lot to say about bigger systems. It looks at individual chunks. So I can say this desktop and that laptop have such and such impacts, but you don't really know much about how people are using the devices and how many of them exist. That's one level above LCA. So you can't answer those kind of questions with this method. In terms of policy relevance, a lot of organizations and governments are moving towards adopting life cycle assessment in their decision making. We're seeing this with carbon footprinting especially, but it's even at the University of British Columbia here, we're thinking about ways to figure out what the impacts of all the pieces of our systems are and feed those into decisions so that we can make decisions that lead to buying greener, reducing impacts. We need to have better methods before that's possible and better data, but there's definitely people are grasping for information in this world. They want to know, organizations really want to know what the green options are, and it's really hard to answer that question. So that's a really vital part of this method. So that's the engineering LCA approach. That's one out of the four I was going to talk about. Number two, energy modeling and energy planning. So what I mean by this, energy modeling is basically the people whose job it is to predict energy loads and predict and run energy forecasts. So these are people like Mark Jackert at SFU, it's the US Energy Information Administration, it's the International Energy Agency, various other people like this, the ones who run big forecasts of energy consumption. And they do all kinds of sophisticated methods. Techno-economic modeling, I think, is what you would call it, where you, instead of looking at individual products, you think about the services people are consuming. Services like lighting and heating and transportation and communication and entertainment. And you figure out, you take an economic perspective, try and figure out what the demand is for these services and how much they cost, and what their prices are going to be and how much of them are going to get consumed. And you try and estimate and model feeding in empirical data how these things are going to evolve in the future. And using that, you develop various parameters relating people's wants and needs to the technologies, and you run those into an economic model and do a big simulation of the economy. And it spits out, this is how much people are going to drive, this is how much lighting people are going to consume, this is how much computers they're going to buy, and so on. And that tells you how much energy they're going to consume, and that's your forecast. It's a very sophisticated method. The models are incredibly complex, and they work at a very high level. It's sort of talking about aggregate population level data here. So we know from this sort of method that households and offices alike spend about 5 to 10% of their electricity on electronics and IT. So in your residence, that's your television and your computers and your game consoles. In an office, it's your computers, your copiers, printers, and your data centers. 5 to 10%. It's, again, not small and not gigantic. It's there. It's comparable to the other traditional energy uses like lighting and heating. So it's something that has to be taken into account for sure. We also know from this field that devices tend to get more efficient over time. You see it happen with refrigerators, ovens, dryers. It's also true in computers. Not that long ago, a desktop PC would draw 200 watts while it was on. These days they draw about 80. And laptop PCs, they draw about 40. Tablets, 5, well, from a battery. There's technology improvement going on, and this is sort of a natural trend. There's all kinds of feedbacks that make this happen. But generally speaking, you can reliably count on things getting more efficient over time. And the model will explicitly include that. They'll model like a 1% energy improvement per year just happening by itself. Like, you don't have to figure out why it's happening, it's just you can depend on it being there. So we know this is true in ICT. We know that a lot of the number of devices in use is growing. Penetration of some devices like televisions and desktops is almost full now, but there's always new products coming out, and you can do modeling here and figure out people are going to buy lots of stuff. So, excuse me. So you have an efficiency trend going down, and you have the number of device trend going up, and those two things are competing against each other, and the net result is a slight increasing trend, 1–2% per year in terms of energy consumption for all these devices. That's what we're able to find out using energy modeling. Some people have done really interesting research comparing energy services to see the impacts of ICT. And one really fascinating area to me is transportation. So there's a theory that goes that transportation and communication can be substitutes for one another. If you have good communications technology, you don't need to travel. You can do a telemeeting instead of flying. You can telecommute instead of commuting physically. And most people think that it's greener to not travel. You can use, if you can meet over the internet, you're going to save emissions compared to if you fly. You can do a life cycle assessment using the previous method and test that assumption, and it turns out, yes, it's true. It is actually much greener to not fly. The obvious result is true. However, that's only part of the picture. The other part is, what are people doing? What are these feedbacks in the economy? How does people's demand for services change by the availability of technology, and so on? And when you run the numbers, you see that travel demand is actually going up. And it's, even if you control for like communications, you can see that the more communications technology you have, the more you travel, not the less, even though you can replace travel with communication. And what's going on is that the more connections you make with people, the more people you talk to, the more reason there is for you to travel to meet them. So you end up stimulating more travel than you end up replacing. So again, there's competing trends going on, right? But all the numbers say, okay, we got more efficient at communicating, but we're actually traveling more than we used to because of this, which is an interesting counterintuitive result. I think it's really important that we do this kind of research and look at high-level trends. Don't just look at the individual behaviors, look at the big picture and how the behaviors interact. Because if you only look at the isolated thing and say it's green to do X versus Y, and don't think of how much people are going to do X versus how much they're going to do Y, you won't get the right answer. Some other work I've been doing is looking at media consumption as an energy service. So especially in the home, how people consume web and video and music and internet stuff, and what devices they're using, and looking at trends I can find from published research and seeing how that affects the network infrastructure that we have to build. And interesting finding that came out of that work is that about half of all the cell phone towers and internet services and cables and servers and data centers, about 50% of that is running so that we can push video into people's homes. People like watching video a lot, and video is incredibly high bandwidth intensive. It's, you know, I don't know if you can picture, like, it takes a lot of internet speed to be able to watch a video smoothly, right? So high definition videos are being pushed everywhere now. And you can trace those trends. There's market research reports that say people's demand for video is going to go up. So something I've been working on is if you actually follow that through, okay, so the video demand is going up, what does that mean in terms of the networks we're going to have to build, and what does that mean for energy consumption? You can kind of see that this desire to have video everywhere is going to drive energy consumption in the network infrastructure we build, which is an interesting way to think about it. So I'm kind of arguing, again, get out of this narrow life cycle assessment view of product X versus product Y, or behavior X versus behavior Y. Look at the big trends about what people are doing. That's the only way you're going to get a reasonable answer. So this is energy modeling. This is what we already understand. We don't really know about data centers. People have measured the energy consumption of data centers. They found it's half of commercial energy in this from electronics. It's like 1%, 2% electricity, something like that overall. How fast is it growing is an unknown. The models say it's going to grow at 1–2% per year. but a recent industry survey said it's growing at 10% per year. And if data center energy is growing at 10% per year, then it's going to become a gigantic consumer within a few years. It's going to like disproportionately grow to be 5 or 10%, and we're going to start competing with transportation and agriculture in terms of our emissions just to run data centers. I don't personally think that's likely, but that's what some of the data is saying, so it's an unknown right now. It's something very important, I think, to figure out. We don't know how new products and behaviors are going to emerge and how that's going to affect people's energy services and their preferences. It's hard to model these things because obviously behavior is complex, so this is a major thing. People are always trying to look ahead. We also don't know the large-scale ripple effects. We can look at things like travel and transportation and communication and look at the interactions between those, but to try and figure out, okay, people are going to travel, they're going to telecommute a bit more, maybe they're going to live further away from urban centers, maybe that's going to affect transportation patterns, maybe that's going to affect the way we build our cities. Those kind of like high-level linkages are really, really hard to pin down in this kind of work. But they're very important, so that's kind of an important area to think about as the big questions. This kind of work is really important from a policy perspective. It feeds into utility load forecasts, it feeds into national energy strategies, it feeds into climate policy. All of the modeling I've been talking about, the IEA, the EIA models, those are the ones that underpin a large chunk of the climate models, the forecasts. So ICT is an important piece in energy models, and those are an important piece in climate policy. So there's definitely understanding the way these things interact and the way they work is a very vital area of research and very difficult. That's number 2, energy modeling. The third area of research I referred to as public health environmental science. What I mean by this is toxic materials, damaging substances, finding problems, especially occupational health problems in industries, public health risks, environmental contamination risks and damage from the tech sector, and especially focusing on manufacturing and recycling industries, which are very important. The methods in this world is epidemiology, toxicology, soil samples, that sort of thing. Very more traditional, I would call physical science and quantitative science, I guess. The point here is to figure out what are the bad things going on in this industry and how do we reduce the damage of it. There's been some really important work done. So what we know from this domain is that we know that semiconductor fabrication is a little bit damaging to workers as risks of cancers, but we know especially that it's the waste, the end of life phase of electronics that's the problem. There's a lot of materials inside these things like lead and brominated flame retardants and other toxins. And some people have done enough studies to show that if you throw these things in landfill, some of these bad materials might leach out into the ground. So for that reason, we have e-waste recycling programs. Even here in BC, we have an e-waste recycling program where you take your stuff to the bins at the Salvation Army or London Drugs. I forget the name of the company that picks them up, but they all, do you guys know about this? You know where they wind up? They go to Teck Cominco, the mining company. They have a smelter in Trail, BC. So all your devices get shredded up and separated and smelted, and the materials are recovered there, and the emissions are sort of captured and minimized. So if you buy a computer in BC, you pay a fee, which funds this program. This is strictly because we think that there's toxic materials that might get into the ground. That's the only reason this exists. And there's e-waste programs all over the world, so this is a major, interesting result. We also know that a lot of electronics end up being disassembled and recycled by hand in lower income countries, especially China, India, Nigeria, Ghana, and maybe that's the main ones. Cynthia's done some work in Ghana looking at e-waste recyclers. We're trying to write a paper about this. We'll see if that happens. There's incredibly damaging environmental things going on in these places. The stuff there's a lot of open burning to melt the plastics and extract the wire. There's acids being used to dissolve things. There's huge environmental contamination, huge public health problems, and there's been lots and lots and lots of primary research done to document these problems. So this is a major, actually, the interesting thing is that how this work feeds into the sky is falling narratives. All the pessimists will cherry pick these results and say, because of these things, technology is ruining the world. I mean, that's a bit of a leap, right? Those conclusions are not part of this research. That's someone else saying that. But this research is a very important piece of the puzzle, I think, to identify what's bad. And especially, sometimes there's alternatives that can be put in place to reduce the use of toxic materials. So we don't really know from this kind of research the global aggregate impacts of the industry. It can't answer that kind of question. And we don't know specifically whose fault something is. We can't say it's an iPad or it's a cell phone or whatever. We can't point to one company and say this is your substance that's showing up in landfill. It tends to all get mushed together. The entire sector is trash, waste. And so it's sort of a sector-wide problem. But in the end, though, these people are all using the same parts from the same factories, which is with different labels on them and different configurations. So it's sort of, there's no judgment to say one company is greener than the other because of this research. It's more like these substances should or should not be present. So policy relevance, as I said, e-waste recycling programs, a huge outcome of this kind of work. There's also a very important piece of legislation in Europe called ROHS, Removal of Hazardous Substances, which has required the transition away from lead-based solder to tin-based solder. So trying to remove lead from electronics. This has come out in the last 5 years or so. And what's happened with that is really interesting. All the electronics companies, in order to be able to sell in Europe, had to be ROHS compliant, which means their supply chains were free of lead-based solder. So they made that transition. They got rid of the lead. But when they did that, they're not going to have two supply chains, one lead-containing and one not. They just transferred everything. So now the entire global sector is lead-free because of the European legislation, which is an interesting leverage point, right? It's kind of nice. It's a good story, I guess. So we don't know, though. We don't know which other materials might be bad. We don't know the impacts of the new solder that we're using. We think it's better than lead, but it's hard to say that. There's all kinds of toxicology, public health work that has to be done to prove these things, and it's a beast of a problem. So that's public health, epidemiology, and so on. The fourth area is the one I know the least about, but it may be one of the more important ones, social science. I hope I'm using the terms correctly here. The goal here in social science, I'm using this as a blanket term. I mean sort of the people who are asking big questions about society and trying to find meaning and trying to understand the long-term trends and trying to understand what trajectory our society is on and what are the basic assumptions underlying what we think we should be doing, and maybe is there adjustments to our trajectory that we should be made. These are the kind of big questions that I'm imagining people should be asking, and there's evidence that they're asking some of these questions. The methods, there's sociologists, anthropologists doing studies of the way people work, the way people's societies are organized. Sustainable development people are kind of all over this. There's a whole subfield called ICT4D, ICT for Development, which is about distributing technologies into developing countries to help them grow their economies and leapfrog out of poverty. There's social justice issues. A lot of people thinking about how people work and whether the industries where people are, let's say, assembling electronics or disassembling electronics are just towards these people and whether they're problematic and whether we should sort of impose regulations or not. And there's people applying all kinds of theories about society and doing sort of long thinking qualitative papers that are really out of my comfort zone in terms of evaluating. So we know from this kind of research already that ICT is a very transformative industry. It tends to accelerate. Whatever path we're on, it's getting us there faster. That's something we understand. So we better make sure we're on the right path, and if not, we better change it because we're going faster and faster because of ICT. It sort of accelerates things. We know that it's economically vital to a large part of the globe. A lot of developed countries have very important technology industries, but a lot of developing ones do as well. In Ghana, for example, Cynthia was identifying how a lot of the e-waste workers are very marginalized people and they have no other options for work. So they're doing very dangerous jobs, but they're earning a living. And if we took that away from them, they would be even worse off than they are now. So at the same time, there's social justice questions. You may have heard of the Foxconn suicides. Foxconn is a huge contract manufacturer in Asia. It employs about 1 million people. It's in China, I forget, Shenzhen maybe. And there's concern that the people that work there aren't treated well because they work 7 days a week and they live in company dorms and they have very little freedom, and some of them are committing suicide. So there's questions to be asked about whether this is just and whether this is the way it should be. it's complicated. I'm not going to answer that. I don't have an answer for it. But we know that there's some issues going on here that we should think about. We also know that the biggest implications of ICT are the big societal shifts that are going on. And these are the hardest ones to answer. So we know basically the most important questions are not really answered, and they're very hard to answer with the methods that we have. In a sense, a lot of the work that's done is reactive. As I said earlier, it's hard to predict what's going to happen, so you just have to play catch up and try and make sense of it as it happens or after it happens. That's kind of the state of this field. We don't really know what's going on next, what's coming next, and what it's going to look like, and we don't really know what to do about it. And these are the big challenges in this field. I think for policy relevance, this is kind of big picture thinking. It influences the way people conceptualize problems. It has implications for e-waste policy, climate policy as well. And but yeah, it's this kind of work. It's harder it's less focused on specific problems, more on bigger questions. So yeah, those are the 4 domains: engineering lifecycle assessment. How green is my product? What's the green alternative, and what are the numbers? Energy planning. What energy services are people wanting? What's the demand for them? How do their behaviors interact with the economy, and how does that drive consumption, and how does that drive energy, and how does that drive climate policy? Then there's public health, environmental science, which is what are the bads, the chemicals, the exposures, the diseases, the death, all the negative things, and how do we reduce those? And then there's the social science, which is the big questions, which is achieving what I would call more limited success to date. So my own research, as I mentioned, I've done some life cycle assessments of electronics products. I've done a bit of work looking at energy services and media consumption and how that relates to network infrastructure. A third piece I haven't mentioned is I'm looking at how energy is used to provide IT services on the UBC campus, and Stefan and I are working together on that one a little bit. So that's the overview of the field and how I fit into it. I'm quickly going to say where I think it's going in the next few years. So there's two parts to this. There's the technology outlook, and then there's the research outlook as well. So what's happening in high tech is an interesting question. Three things that I'm going to mention. First, ubiquitous computing. A lot of people think that we currently have laptops and tablets and phones and computers and televisions. A lot of people think the boundaries between these products are going to blur even more. We're going to have displays that we interact with everywhere. They're going to be like roll-up displays that come down from the walls. Your computing sessions and your computing power is going to be distributed. It won't live in any one device. So that means more devices, more products, more data being flown back and forth, more video, everything more. So all the trends of everything growing is going to keep growing. Number 2, the Internet of Things. There's a holy grail in computing which revolves around creating very tiny wireless sensors that can take readings of some data and transmit it wirelessly to some sort of central system, including spatial coordinates. And you can have kind of a big web of sensors that are instrumenting the world. These already exist to some degree, but they're going to get better and smaller, and there's going to be more of them. And eventually your entire home is going to be instrumented, and you'll be able to see precisely who's consuming the energy at what time. I mean your toaster or your air conditioner or your lights. You're going to be able to, industrial processes are going to have very, very precise knowledge about what kind of emissions are being released and how much energy is being used. And it's going to be much easier to track materials. We're just going to have basically a lot more knowledge about what's going on around us as these things get deployed more. And this is 5-10 years out. We're going to start seeing this. And then number 3, big data. This is a revolution going on right now, and which is going to continue. The more we instrument things, and the more sort of computer systems we have monitoring stuff, the more data we get about the world and about people's lives and people's decisions and behaviors and about what people want to do and how they consume and about how energy is consumed and how resources are consumed. There's a lot of buzz right now about ways to process mountains and mountains of data to derive insights about people. This is kind of an emerging area, and it's going to be hugely relevant in this space and in many other spaces. Smart meters are a good example. We're going to have very good metering on every house in BC through the smart metering system, and that means we can run really sophisticated stats and figure out a lot more, gain a lot of knowledge about how energy is being used. Once we start instrumenting homes with sensors everywhere, we're going to have even more. So software techniques to handle data and is going to be a very important driver in the tech space. Research needs within the 4 areas. Lifecycle assessment, as I said, is usually playing catch up. It's using old data, it's analyzing old products. It has trouble gaining traction as a reliable method because of the data problems and the uncertainty. I think it's going to be helped out by the Internet of Things, by better instrumentation and open data protocols. There's sort of convergence happening in this space a bit. It's going to need this stuff to stay relevant because it's never going to be able to keep up with the change in products. That's sort of it's not going to work very well. So I'm hopeful maybe that lifecycle assessment might find ways to capitalize on improved data out there. I think that's where this field needs to go. Energy modeling and climate policy is going to have to deal with all the new products, keep trying to figure out how people are behaving. It can be a major beneficiary of improved data coming in because you can make more sophisticated models and get a better idea of people's preferences, which is the key challenge in energy modeling. So that's, I'd say, figuring that out and finding out what the opportunities are and how to capture them is the key challenge coming in energy modeling. Public health and environmental science has to worry about toxic materials. The tech sector has always been a very early adopter and innovator in the use of exotic materials. Something like 3/4 of the periodic table are inside every one of your laptops. There's thousands of chemicals being used, and they're way behind the game, again, in terms of what are the dangerous substances and what should we worry about. So they're going to have an increasing challenge to stay on top of and figure out what are the bad things that we should not be doing and how do we find good alternatives. That's a huge research need there. And then social science, as I said, the big questions are largely still up for grabs. We're going to continue to see rapid disruptive change in the foreseeable future, and grappling with that, understanding what it means, is going to be an ongoing problem. Excuse me. So that's about it. Just the takeaway messages, I guess, is that the sky is neither falling nor not falling. We're not going to save the world with tech. We're not going to destroy it with tech. It's just a piece of this bigger puzzle. This much is sort of clear now, I think. It's just one of many things going on in our world, and more traditional methods are useful here. There's a lot of work to be done quantifying energy and materials impacts, reducing them and stuff. That's definitely very vital, but I think the bigger questions about how society is changing are maybe the more important ones and places that are in more need of attention. That's it. Thank you very much. (1:48). Got to run in a few minutes, but any questions?